Hi everyone, I'm Yifeng Cao from Georgia Tech. I will briefly introduce my project Homecoming here. As we can observe, delivery service providers are on the way to invest money on the drone-based delivery service. Recently, Amazon Prime Air has been certified by Federal Aviation Administration, making one more step to the commercial use of drone delivery service. In this project, we focus on this problem. How does a drone identify and land on a landing zone properly? One way is to use the drone cameras. The landing zone will be labeled with a special mark. By running CV algorithm on the drone identifies the landing zone and lands on the ground. While camera is widely used, this kind of solutions expose some weakness. From another side, we observe the emerging of lots of RF-based localization technique. It has some good property which can overcome the weakness of camera-based solutions. So we believe it is very promising to be the future of drone delivery service. In this project, we built up a small RF-based auto-landing system named Homecoming for the landing of the drone. Homecoming uses ultra-wideband signal with 1 GHz bandwidth and 4 GHz carrier wave. The UWB device also has an accurate clock which can provide nanosecond level precision in time. It can also provide good resolution in channel impulse response. Nanosecond level precision in time measurement makes it possible to calculate the distance directly from time of flight, but naively used them will incur synchronization problem and clock drift problem. So we adopt two-way ranging to optimize the distance measurement. We measure the time gap between sending and receiving three different types of messages, poor, response, and final, and use them to compute time of flight. This time of flight is free from synchronization and drifting problem. With a nanosecond level resolution, the accuracy of distance measurement is about 30 centimeters for one sample. By averaging multiple packets, the error can be reduced to 10 to 20 centimeters. After getting one distance measurement, to identify the landing zone, the naive solution is to place multiple receivers in the landing zone and measure the distance respectively, and then do the multilateration. However, this solution will incur significant errors because of dilution of precision problem. Intuitively, if we use three distance measurements with each with 10 cm independent error, the localization errors will certainly be amplified after multilateration. This can also be visualized in this figure on the slide. The error of the century and boundary area can reach up to 80 centimeters and 2.5 meters respectively. To mitigate this problem, we wire different antennas to the same board instead of using different boards, and each antenna has different delays to avoid the interference with each other. Then we leverage the channel impulse response to identify the received signal in each antenna. Once we identify the signal, we can measure the phase of each signal. The phase difference among peaks is directly associated with the air path difference from the transmitter to the different antennas in the receiver. And fortunately, the precision of this phase is as high as 10 degrees, which is equal to about 2 millimeters after translation. So our ranging approach measures the absolute distance for the first peak. It leads to about 10 centimeters error. Then we measure the relative distance difference between the first and the other two peaks. This relative distance difference has only 1 centimeter error. By doing so, the problem of DOP is effectively mitigated. We test Homecoming with DekaWaveTrack 1000 drill kit in a 10 meter by 10 meter environment. We use naive multilateration as the baseline. The results show that Homecoming outperforms the baseline in all test cases. Certainly, there remains quite a lot of space for this project to go in the future, and I'm here to look forward to every suggestion from you. Thank you very much for watching.